My dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 406. In this lecture, I will continue my discussion on cases of decision trees. And other very interesting thing is called feature interaction in decision trees. Feature interaction basically means, suppose if I am constructing a decision tree with sepal length, sepal width, petal length and petal width. Here I will get non-linearity like this, because if my first decision says PL is less than 3, just see first decision, what is this? PL is less than 3, and my second thing says SL is greater than 5. Suppose I have these two regions, this region and this region. To reach this region, to reach these regions, what I have to do? You have to test these two conditions. Which conditions? PL less than 3 and SL greater than 5. This is called feature interaction because I have two features which are interacting for me to decide the class label. Feature interaction comes as an added inbuilt benefit of decision trees. Now comes the case of outliers. What happens if you have outliers? This is a very tricky case because as depth increases, as depth of my decision tree increases, an impact of outlier is slightly significant. Outliers will impact because as your depth increases, I could have a case where I reach here, where I can reach this particular point, where I reach here, isn't it? I could have a case where I reach here, where I have 2 points. How many points here? We have two points, and both of these points are outliers. Let me assume both of these points are outliers. Especially when the depth is large, outliers will impact. My tree will become unstable. Basically, if these 2 points did not, let me assume, if these 2 points did not exist in my training data because I overfit, if these 2 noisy points did not occur in my training data, this whole part of the tree, this whole part of the tree would not have been here, isn't it? So my tree would change if these 2 points were not there. That's what it is called tree instability. Especially when you are building a tree, building very deep trees, outliers will impact your tree dramatically and it will make your tree unstable. What about interpretability? What about interpretability? Decision trees are super interpretable, isn't it? Decision trees are super interpretable. You can write everything as if-else conditions. It is super interpretable. Suppose if I am a doctor and if you give me some data about cancer patient, let me say the data about cancer patient is XQ, and if I am calling this patient as YQ because has tumor width is large, you can keep in if-else conditions as tumor width may be large, tumor width is large because so and so test turned to be positive because this blood glucose level is this much, and some other test gives the results, and I am declaring YQ to be this. What is the YQ? Depending on those things, you can declare YQ as cancerous or non-cancerous. It is extremely useful because these are extremely readable, especially when the depth is small. When the depth is not large, when the depth is reasonable, now the question is, what about feature importance, isn't it? What about feature importance? It is before again let me repeat about interpretability. Decision trees are super interpretable. You can write everything as if else conditions. Suppose if I am a doctor and if you give me some data about cancer patient, let me say data about some cancer patient is XQ, and if I am calling this patient as whether it is cancerous patient, non-cancerous, depending on YQ will give the label of the patient. Just it is extremely useful because these are extremely readable, especially when the depth is small, when the depth is not large, when the depth is reasonable. Now the question is, what about feature importance? Can we do feature importance for decision trees? There is one way to do feature importance. For every feature Fi, I compute what is the reduction in entropy H or in Gini impurity Iz. What is the total reduction? Because at every node, suppose at this node, at every node, just see, suppose at this particular node, suppose at this node, isn't it? So let me repeat, there is one way to do feature importance. For every feature Fi, I compute what is the reduction in entropy, H or in Gini impurity Ig. What is the total reduction? Because at every node, suppose at this node I use feature Fi to break it, I got some information gain which is nothing but reduction in entropy. Suppose at some other level I can sum up or add up the reductions in entropy due to the feature Fi. I can sum them up smartly. Can I sum them up? Yes. Now, not like brute force sum. There is something called normalized sum. We have to do normalized sum, but intuitively what it means is, if a feature found lot of times in your decision tree and it's reducing entropy lot, across multiple levels, then that feature is very important. Actually, lot of toolkits, including sklearn, you might have heard this sklearn, lot of toolkits like sklearn. When you train a decision tree, for each feature Fi, they give feature importance, which they measure using how much reduction there is in entropy. Because this feature, how much reduction is in entropy because of this feature, how much this feature Fi helping us to build the decision tree, because this feature only will be used when it reduces entropy, isn't it? When can I say? Because the particular feature only it will be useful when it reduces entropy better than other features. Computing feature importance is very straightforward in the case of decision trees. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.